Here's something you do every single day without a second thought. You turn a wheel in your hands, and two lumps of rubber and steel out on the road obediently swing left or right. But how? There's no direct rod bolted from your hands to the tires. So what's actually translating that spin of the wheel into a precise change of direction? Stick with me, because the answer is a beautifully simple bit of engineering that hides one genuinely clever trick most people never notice. Nothing's free. Hydraulic steering gave you rich, direct feedback. You could literally feel the front tires talking to you through the fluid. Early electric systems felt numb and artificial by comparison, and enthusiasts hated them. But engineers have clawed most of that feedback with better sensors and software. And step back and marvel at the whole thing. A pinion the size of a thumb, a toothed bar, two rods and geometry from 1818, all combining so a gentle turn of your hands guides 2 tons of your hands guides 2 tons of metal exactly where you want. Simple parts, brilliant thinking, and you use it every single day. Most cars built in the last 15 years use electric power steering instead. An electric motor, often wrapped right around the steering column or the rack itself, reads a torque sensor that measures exactly how hard you're twisting the wheel, then spins to add precisely that much help. The huge advantage, it only draws power when you're actually steering, saving fuel, and it can vary the assistance with speed. Light and easy in a car park, firm and stable on the motorway. It's also what makes lane keep assist and self-parking possible, because now a computer can turn the wheel too. Clever. But what did we give up? A modern car's front end might carry over 60% of the vehicle's weight, and shoving that around by twisting a little pinion is hard work. So we add assistance. The old way was hydraulic. An engine-driven pump pressurizes fluid, and a clever valve around the pinion senses which way you're pushing, then feeds high-pressure fluid, often over 100 bar, to one side of a piston built into the rack. The fluid does the heavy shoving, you just point. It's beautifully responsive, but it's always running, always sapping a little engine power, which is exactly why newer cars threw the pump away. Here's how that trick actually works. The steering arms don't point straight back, they're angled slightly inward, so if you drew a line through each one, they'd meet at the center of the rear axle. Because of that angle, when the rack slides, the linkage geometry naturally forces the inside wheel to turn more than the outside. No sensor, no computer, just the shape of the linkage doing the maths for you. That's what I love about mechanical engineering. The intelligence is baked into the geometry itself. But there's still one problem left. Turning that pinion by hand takes real effort, especially when you're parked. This is the bit that genuinely surprised me the first time I understood it. When you go round a corner, the inside wheel is tracing a tighter circle than the outside wheel, a smaller radius. If both wheels pointed at exactly the same angle, one of them would be scrubbing sideways, fighting the turn, chewing up your tires. So engineers deliberately make the inside wheel steer a few degrees sharper than the outside one. It's called Ackermann steering geometry, patented back in 1808, and they achieve it not with electronics, but purely by where they place the steering arms. Each end of that sliding rack is bolted to a slim rod called the tie rod, and each tie rod reaches out to a steering arm sticking off the wheel hub. So when the rack shoves left, it pulls one tie rod and pushes the other, and both steering arms swing the same way. The tie rods end in ball joints, little spherical pivots, because the wheels are also bouncing up and down over bumps at the same time. Those joints let the rod push sideways while still flexing vertically. It's a genuinely elegant chain, gear, bar, rod, arm, wheel. But here's where it gets clever. Both wheels can't simply point the same direction. Here's the core of it. At the bottom of the steering column sits a small round gear called the pinion, usually just a few centimeters across, with maybe 7 or 8 teeth cut into it. That pinion meshes with a long flat bar covered in matching teeth called the rack. When the pinion spins, its teeth walk along the rack's teeth, and because the rack can't rotate, it's forced to slide sideways instead. That's it, that's the whole trick. Rotation in, linear motion out. The rack might travel around 15 centimeters end to end. Now, how does a sliding bar become 2 turning wheels? Think about what steering actually has to do. Your hands spin a wheel, that's rotary motion, going round and round. But the front tires don't need to spin about a vertical axis endlessly. They need to swivel, maybe 30 or 40 degrees each way, and then stop. So the very first job is converting a rotation into a controlled, limited side-to-side movement. Early cars used all sorts of clunky worm and sector boxes to do this, heavy things full of gears. But there was a simpler idea waiting. And it comes down